Yeah, welcome everyone to the robust optimization webinar of this week. I'm very happy to have Paul Grigas here, who is associate professor at the University of California, Berkeley. He received his PhD from the MIT in operation research, and his research is focused mostly on optimization, machine learning, and the intersection of both. So he's very well known for his paper on smart predict and optimize together with Adam Almachtub. Um, and yeah, he's also affiliated with the AI for Opt Institute and won several awards already. One, just to mention one, he got the first place in the 2020 Informs Junior Faculty Interest Group paper competition. And I'm very happy to have you here, Paul. So please.
Thanks so much. Thanks, Giannis, and for the introduction, and thank you, Giannis and Amadreza, for organizing this great webinar. So this is a great service for our community. So I'll be talking today about some work that is again situated at the sort of intersection or interface between learning and optimization, specifically on parametric optimization. So it's a little bit adjacent to robust optimization, not exactly related or looking at robust problems, although I'll mention some extension to some robust optimization problems, as well as some connections along the way. But the majority of the talk will be about this parametric optimization beyond discretization subject, which is the topic of a paper with with two collaborators, Shiran Dong, who is a PhD student at Berkeley, and Vishal Gupta, who's faculty at USC Marshall. So 95% of the talk will be about my joint work with them. And I'll mention, as I said at the end, some other extensions and connections to other related work, including some work that more directly looks at robust optimization problems, which is joint with Wiem Benselmane, who's another student in my group. And also I'll mention some other related work with a former student, Hei-Wan Liu. So all of these works are kind of broadly related to a similar theme around the interface of learning and parametric optimization. But again, the majority of the talk is going to be about an example of one paper in this theme, which is joint with Shiran and Vishal. Okay, so I'll start with introduction and discuss some motivation and sort of set the stage with some preliminary discussion. And then after that, I'll introduce the main method, which is we call learning the optimal solution path. And then I'll discuss some of our guarantees for that, and also um, uh, so I'm sorry, I just want to make sure I have the clock somewhere here. And it's not showing up for some reason. Okay, I think no, that's good. Okay, so then I'll introduce the main learning the optimal solution path method, as we call it, and discuss the sort of the formulation, the recipe for our algorithm, and then the theoretical guarantees, as well as numerical results. And then I'll get into a little bit briefly this discussion of some related work, and then give some conclusions and have some time for questions. Okay. So parametric optimization is really common in probably all applications. Broadly speaking, right, we can think of parametric optimization, very broadly as optimization problem with some parameters that appear in the problem that are not decision variables, right? So that's a very broad definition, and so then it becomes useful, I think, to distinguish, some sort of taxonomy of different parametric optimization notions, right? So it's useful to distinguish between endogenous and exogenous, as well as known and uncertain parameters. So this talk will be primarily about aspects of parametric optimization where these parameters appear either endogenously or are somehow known in the decision-making process. So it's not directly tackling optimization under uncertainty. However, as I said, there'll be some extensions that will look at some uncertain problems as well as some connections to notions, I think, in robust and stochastic optimization. But directly, we're going to be addressing sort of parametric optimization problems where these parameters are either something that are endogenous parameters that somehow must be tuned by the decision maker, or they're somehow variables that are known, like state variables in a control problem. So think of situations like multi-objective optimization, where you have multiple competing objectives and some parameter that controls the trade-off between these different objectives. Human-in-the-loop decision making with optimization, where feedback from a human must be used to somehow tune these parameters, and human may be, not totally clear about what their preference is on these different parameters, and so observing things like a Pareto frontier or somehow visualization of a trade-off between these different metrics may be useful. Hyperparameter selection in machine learning is another example. That's a little bit more concrete in the sense that usually there is some sort of notion of best parameter given by some cross-validation error or some other out-of-sample type of performance metric. In that sense, it becomes often modeled as a bi-level optimization problem. So we want to kind of go beyond that a little bit, although it's an example, I would say, of parameters appearing in the optimization problem. We really want to, in this talk, think about situations where it's important to actually compute the optimal solution across all values of the parameters, right? So situations where computing the whole Pareto frontier is important, or situations where we really do need to compute optimal solutions across all values of the state parameters, and so forth. So that's the kind of parameters that I'm thinking about in this problem. And I'll give a few more concrete examples. So think about a classic portfolio optimization problem. The Markowitz portfolio optimization model, for example, it's a classic model that trades off between expected return and risk of the portfolio, as well as possible other terms in the objective function, such as some form of regularization or transaction cost or something like that. This is a situation where it's very well known that decision makers do not necessarily, a priori know the parameters lambda here in the objective, right? Lambda 1, lambda 2, and lambda 3 represent the parameters. Decision makers don't really know their parameters necessarily ahead of time. But if you show them some scenarios, you show them a frontier like the frontier in this slide, they may be able to use these kind of visualizations and surveys and other sorts of decision tools to implicitly figure out what their parameters are, right? And so to be able to offer these sort of visualizations or these sort of decision support tools, we need to be able to compute many, many solutions of this optimization problem across all values of these lambda parameters, right? And again, it might be more than just these three. It might include other terms as well. For another example, we can go to machine learning, but not the hyperparameter tuning case, like where we're thinking about a regularization parameter, but machine learning or just simply binary classification, where we have different costs on the mistakes that we make on the different classes, right? So the classic case in binary is you only have two classes, so there's a trade-off between false positive rate and true positive rate. And this trade-off is we want to maximize true positive rate and minimize false positive rate. And so the trade-off is visualized in this kind of ROC curve. And of course, that extends to the multi-class case where you just look at the number of mistakes that you make on each class or some other loss metric on each class. And you minimize an objective over your model parameters that considers a weighted sum of the combination of losses on the different classes, right? And so in the multi-class problem, we may care differently about the performance on each class. And it, again, may not be totally obvious to the decision maker ahead of time what the trade-off between the errors on the different classes really should be. And this is why things like ROC curves are really popular in practice, because this allows the decision maker to visualize that trade-off And ROC curves are often computed in a kind of heuristic way, based, for example, on varying the threshold in logistic regression. But they can be computed in a more rigorous way, perhaps, by really solving an optimization problem like the one I've written on this slide across all values of the relevant trade-off parameters between the different classes, right? If you really find the best possible solution for all values of that parameter, you can draw a very good ROC curve, right? And so this is another case. And again, we may also care differently about beyond just the errors on the different classes. We may also care differently about performance in different subgroups of the population, for example, which is something that shows up in fairness. Finally, I'll give one more example, which is related to some project that I've done with some students and some staff here at Berkeley that manage our Fung Institute, which is the institute that manages the Master of Engineering program. And so this program involves a capstone project where teams of students are matched with different advisors, either faculty or industry advisors who run capstone projects. And prior to our work, they were really not doing anything very sophisticated to match the students to these projects. Now we've implemented a matching algorithm that solves an integer program, and it involves a objective function that has at least six different performance metrics, each of which is weighted by a different parameter lambda. And this is because there are a lot of considerations that go into how to determine a good match, and a lot of different stakeholders, each sort of with their own goals. So this is a situation where, in fact, we had to build for them not just the optimization model, but also a sort of decision support tool where they can visualize the solutions to the optimization problem, the matches that are output, and understand the different performance metrics, and quickly generate new solutions, and try to determine what is a good match by playing with these parameters through this decision support tool. So this again is a situation where one needs to compute the solution very quickly to this optimization problem across all values of these lambda parameters. Okay, so with these sort of examples out of the way, let me now get into the formulation. So I'll consider in this talk a relatively simpler setting than some of the examples where I consider unconstrained parametric optimization problems. Constraints can be dealt with by adding penalty functions in a soft way, or perhaps with more sophisticated methods. But this talk will be primarily about establishing some theory for a natural learning-based method in parametric optimization. And so to establish the theory, it really helped us to start with the simpler case of unconstrained optimization. So specifically, we'll look at parametric optimization where our decision variables are theta and the parameters are lambda. And we have an objective function h that depends on both theta and lambda. And for any given lambda, we want to minimize this objective function with respect to theta. So we want to compute what we refer to as the solution path or solution map, which is the mapping from lambda to theta star, right? So theta star of lambda for all lambda in some set of interest, capital lambda. We call this solution path primarily because of the existing literature, which focuses a lot on the one-dimensional case. But in our case, actually, lambda can be multidimensional. So there's not necessarily any structure imposed on lambda a priori. It might be a multidimensional vector. Nevertheless, though, to be consistent with the literature, and we call it solution path. But you can think solution path or solution map. Okay. So this is our goal, right? Efficiently compute this solution map or solution path theta star. And this gives a sort of formal definition of that solution path or map. And of course, our challenge is that nearly exactly computing theta star of lambda is computationally expensive. We want to really understand the computational complexity of computing this solution path, this solution map. So how do we, first of all, measure our progress, right? How do we measure our, what is our criterion for having a good solution map? We're in situations where the parameters are either endogenous or somehow known parameters to us, and all of these parameters matter, right? So we do need to get good solutions for any of these parameters, and so therefore we really want to impose that we find an approximately epsilon optimal solution for all lambda in the set of interest, right? So we define an epsilon solution path theta hat as a mapping which produces a solution that is at least epsilon close to the optimal theta star of lambda for all lambda in the set of interest, right? So our notion of epsilon optimality is that you must have an epsilon suboptimal solution for all lambda in the set of interest, right? And our key question will be, what is the complexity then of computing an epsilon optimal solution path for any given epsilon positive, right? And so to think about a picture in your mind, something like this can be helpful, right? So this is the one-dimensional case where really we are talking about a path. In multi-dimensional lambda, you have a surface in a higher dimension, but here we're talking about in this picture, one-dimensional lambda, and so the exact solution path is in yellow, right? It's the set of exact optimal solutions, and we can think of an epsilon solution path, right, as corresponding to any approximately a close solution path measured in objective function, right? So think about a small band around the exact solution path that corresponds to these epsilon solution paths. Okay, so then what is the sort of like default approach that people will take? Well, especially in the one-dimensional parameter case, discretization, right? So it's the most natural idea. So you take your set of possible parameters and you form a discrete approximation to that set, and you solve your optimization problem at each discrete value, and then somehow interpolate between the solutions, right? So a very natural idea, but key sort of observation is that discretization is a local method, right? So discretization only chops up the sort of interval on lambda and then only solves each problem locally and kind of forgets about the overall global structure of the solution path. And so of course we want to not forget about that, right? So we want to examine, if it's possible to sort of leverage the global structure of the solution path to develop a better methodology. And so that's really one of our key motivating questions, right? Is, can we develop a method for approximating the solution path that sort of leverages this global structure and also works for arbitrary parameter spaces, capital lambda, right? So it goes beyond just the case of one-dimensional lambda that I showed in that picture. Moreover, we take the perspective here in this work of looking beyond the local model of discretization in terms of complexity theory, right? So the complexity theory of discretization essentially asks, how many discrete points do I have to determine such that if I solve the optimization problem at each of these discrete points, then and interpolate the solutions together, then I recover an epsilon solution path. That's a model where the basic building block of the complexity is solving individual optimization problems. But these individual optimization problems are not independent of each other, right? They are related to each other through lambda. And so to have a better analysis, then we want to consider a more fine-grained computational model that really looks not just at how many optimization problems do you solve, but what's the actual work involved to solve each of those problems. And we will do that in the case of gradient algorithms. under convex objectives, as we'll see. Okay, and perhaps in the case of a single hyperparameter, we may be able to better leverage the structure to develop even and better enhanced algorithms that truly improve upon the complexity of discretization in theory and in practice. Okay. So yeah, the way that we'll answer these questions is through our flexible learning the solution path procedure that will work for an arbitrary parameter space. It will prove that it converges up to a certain notion of approximation error for smooth and strongly convex problems. And we'll analyze its complexity, the complexity of our overall algorithm in particular, through a gradient oracle complexity model that will be more fine-grained than the complexity analysis of discretization, right? So we'll be able to say not only how many optimization problems do you need to solve, but actually what is the overall work. And importantly, we'll show that the overall work in certain cases is strictly better than the overall work required for discretization. Let me briefly mention some related literature. So most of the related literature directly addressing this type of parametric optimization problem, as I mentioned, is looking at the one-dimensional parameter case. And there are works, specifically this 2019 paper of Nidiayi et al., that theoretically studies the complexity of discretization. And again, as I mentioned, their model is, like I said, it analyzes the number of discretization points that you need to have in order to interpolate them and then solve the obtain a solution path. Right. So each discretization point, you're solving the optimization problem exactly. And so the black box there becomes a discretized problem, and we want to make our black box more fine-grained and look at the gradient oracle complexity. There also is a rich literature on path following and other specialized algorithms when the solution path has some special structure. Classic example of this is lasso regression and related problems. Here we're looking at quite a generic setup. So these sort of algorithms will not apply. But of course, if you do have a very specialized structure to your problem, then these approaches may be beneficial. I also want to mention relationship to some broader work on the interface of optimization and learning. So here, I cannot do this justice in one slide. This is just a quick summary of some related broad areas. And so there are several other lines of work investigating, I would say, approximating the solution map with learning or approximating optimal solutions with learning. So Pascal Van Hentrick and his collaborators have looked at this. They call this optimization proxies. Brandon Amos has a survey called Amortized Optimization with applications in learning and control, etc., where in their works, they're looking at a similar idea of using learning to approximate the optimal solution. However, an important distinction between their works and ours is that a typical primitive in those works and many others is an exogenous distribution over the parameters. So it's typically assumed that you have some distribution over the parameters in your optimization problem, and you care about solving your optimization problem only on that distribution. Right? That is the typical situation of learning to optimize. Here, we don't have such an exogenous distribution, right? We actually have a metric, which is the worst case metric with respect to trying to find an epsilon solution map across all values of the parameters. So our paradigm is a bit different. And in fact, as we'll see, our work can perhaps be thought of as a way to think about how to define distributions in situations where you have the control over what the distribution can be. So in that sense, we give some sort of prescriptions about how to design or engineer the distributions. There also is a wider literature on integrating learning with optimization modeling, which I have contributed to, as well as several others, including people in the audience, and so works on decision-focused learning and contextual optimization, as well as connections to things like decision rules and policy approximation and adjustable robust optimization. These are situations where you want to learn some kind of mapping from or determine some kind of mapping from parameters to solutions. But the criteria again and the sort of setup and primitives of those works is a bit different from ours. Okay. With that, let me get into the details. So our problem, as I said before, is to determine the complexity of computing an epsilon solution path, and so to theoretically study this, I'm going to make some extra assumptions on the objective function. So we consider the convex case where the objective function h as a function of the decision variables theta is mu strongly convex and L smooth for each lambda, right? So, and I noticed now that I forgot the dependence on lambda in this inequality at the bottom, but for each lambda, this function h will satisfy uniformly mu strong convexity and L smoothness. So the assumptions are primarily on the dependence on theta. There's no strong assumptions that are being made about the dependence on the parameter lambda, right? So lambda again can be a vector, and it can be the set of possible lambda of interest is sort of arbitrary and possibly multidimensional. Okay, so in a nutshell, our algorithm, learning the solution path, consists of this sort of four-step recipe. So we're going to try to apply learning to the problem here of computing a solution path. So to do learning, we'll pick some function approximation class, right? In our case, linear combinations of basis functions will be what we primarily focus on for theory. We'll pick a distribution over the parameters lambda. And then we'll sort of glue together this function class and the distribution to construct what we call a surrogate stochastic optimization problem. So the stochastic optimization problem is not a natural primitive of our setup, but rather something that we engineer based on the choice of distribution and the choice of function approximation class. We then solve this surrogate problem with some algorithm, for example, stochastic gradient descent, and return our solution map by looking at the set of the combination of basis functions that is returned. Okay, so going back to this illustration, our idea in a nutshell is to approximate this solution path in yellow with basis functions, right? A linear combination of basis functions. And intuitively, in a picture like this, where the solution path is nice and smooth, such an approach we think should work well because linear combination of, for example, polynomial basis functions can well approximate such a smooth solution path. Okay, so formally we'll fix some basis functions. We call these phi. So phi j for j equals 1 to p are these basis functions. It's assumed implicitly that they're sort of easy to compute for any lambda, right? And we have again p of them from j equals 1 to p. For example, think of polynomials, like in the case of d equals 1, meaning that the dimension of the decision variable is only 1. The Legendre polynomial basis corresponds to this particular basis of polynomial functions, right? Each of these individual functions, and by the way, we organize these basis functions in a matrix, which is a d by p matrix. And again, d is the dimension of the decision variable, p is the number of basis functions. So in the case of d equals 1, the Legendre polynomial basis corresponds to this matrix, which has one row and p different columns. And again, it's a set of specific polynomials. And each of these polynomial functions is sort of easy to compute. And we want to form ultimately a linear combination of these polynomials. Basis functions may seem kind of restrictive, but in fact, a wide variety of learning methods sort of boil down to basis functions at the end of the day. So polynomials, like I already mentioned, also splines, kernels, boosting, in even neural networks can be thought of as basis functions. In the story with neural networks, of course, is that the basis is learned. So it's not just using some prescribed basis functions, but sort of at the last layer, if you kind of freeze the network and only look at the last layer, what it boils down to is basis functions. So in some ways, our results also apply to neural networks. Okay, But in our case, to keep it simple and to understand, theoretically what's going on, at least initially, we focus on a fixed basis function class. And then our idea will be to approximate the optimal solution path with a linear combination of these basis functions. And so I use the matrix vector notation to write this linear combination. So the matrix phi of lambda multiplied with beta gives the linear combination of basis functions. And so our goal then will be to identify a coefficient vector beta, right, such that the linear combination is an epsilon solution path according to our definition, right? The approximate function, which is given by the linear combination of basis functions, is within epsilon of the optimal theta star measured in objective function value. Okay, for convenience and perhaps to understand it even better, we can restate our goal in terms of a metric or criterion that we call the solution path error. It is simply the worst case supremum error of the objective function gap over all lambda. Right, so we call this solution path error or the SP error, epsilon SP, which is a function of the coefficient vector beta, and it returns the maximal, right, supremum value of this objective function gap over all lambda in the parameter space. Right, so what is the worst case error in objective function value for your given approximator over all lambda in the set of interest? So our goal then of identifying an epsilon solution path is equivalent, of course, to looking for beta, right, such that this solution path error of beta is less than or equal to epsilon. So why is this useful? Well, the first thing is that it gives us a way to conceptualize the best possible solution path error that we can achieve. Right, so we call this the SP error star or the approximation error simply, which is the smallest value of the SP error over all possible beta, right? All possible coefficient vectors. So this is sort of an intrinsic lower bound on achievable epsilon, right? We cannot achieve any epsilon better than that for any fixed basis function class. In addition, right, this also provides maybe an idealized optimization problem that we'd like to solve, right? So the idealized optimization problem would be to actually identify a beta that minimizes this SP error over all possible beta, right? Unfortunately, this is not a problem that we can solve. And the reason is that the objective function here, right, the SP error depends on the theta star oracle, which is unknown to us. Right, the theta star oracle is something that we cannot compute. That's our goal, in fact. So we can't really work with this objective function directly. And so this motivates our second ingredient, right, which is to replace the worst case with an expectation. Right, so directly minimizing the solution path error is difficult. Instead, we fix some distribution p lambda over the space lambda and construct a single stochastic optimization problem that minimizes the objective error over this distribution. So lambda tilde coming from this distribution p lambda. So conveniently, when we do that, the dependence on theta star goes away. And we can now just solve this stochastic optimization problem. I want to also point out that this has some other advantages, right? So this the basis function approach sort of leverages the global structure of the solution path, as I already mentioned. This approach also naturally accommodates complicated hyperparameter spaces. So we really used very little about the structure of lambda. Any space where we can put a distribution on that space sort of works. And the algorithm is to solve this stochastic optimization problem approximately. So we can solve it with any stochastic optimization method, right? So it's quite flexible in that sense. So the key ingredients to the construction are the distribution and the basis functions, right? And of course, for the distribution, to be able to apply an algorithm algorithm to solve this problem, we need to generate some samples in an easy way, or otherwise have some ability to do quadrature methods or work with the distribution. But let's just say, for simplicity, to apply something like SAA or SGD, it's easy to generate IID samples from this distribution. Right. At the same time, right, the basis functions need to be some sort of objects that we can easily work with and easily compute. So then a natural question is like, how do these two choices interplay with each other, and and how do they impact ultimately our goal of computing an epsilon solution path? To answer that question, it's useful to define some constants which give us a sense of the condition number of the basis relative to the choice of distribution. And so the right sort of condition number for us to analyze this basis these basis functions relative to the distribution turns out to be this this condition number, big CP over little CP. So big CP here is the largest value, largest over all lambda singular value, maximal singular value of this sort of uncentered covariance matrix type of thing, right? Where you look at the phi matrix transpose itself, and you take the largest singular value, and you actually look at the worst case over all lambda. Little CP is not quite as conservative, so it looks at actually something that really is more like the uncentered covariance matrix, where you look at the expected value of this matrix and take the smallest singular value of that. So the ratio of big CP over little CP will serve as some kind of condition number for us, which will show up in our analysis. And intuitively, it measures for us the complexity of the basis function class sort of relative to this distribution. And we can also identify sufficient conditions to get this condition number to be finite via linear independence like assumptions. Okay, so then given those definitions, let me now introduce our sort of main theorem for relating the suboptimality to solution path error. So again, our surrogate stochastic optimization problem is what we'll solve. And suppose it has an optimal solution, beta star average. And recall that epsilon star SP is our notion of approximation error, right? It's the optimal value of the worst case problem, right? The problem of minimizing the SP error over all beta. And so we want to relate this SP error, right, to the stochastic optimization error. That's sort of the goal of this theorem. And we're able to do that, in fact, by breaking down determining an upper bound on the SP error for any given beta, which will decompose into these two different terms. So let's sort of break down these two different terms, right? So what we show is that the SP error for any given beta is bounded by a term which is proportional to the distance squared from beta to beta star average, right? So that's a notion of optimization error for the stochastic optimization problem. It tells you how close you are to the solution of the stochastic optimization problem up top. Right, so the closer that you are, the better you solve the stochastic optimization problem, the more you can drive that term to zero. On the other hand, there's another term, which we call the approximation error term, which is proportional to that notion of approximation error, epsilon star SP, which is not vanishing as you solve the stochastic problem better, right? So so it's actually basically the condition number that we had before, multiplied with the condition number of the objective function, which is L over mu, multiplied with this SP error, epsilon star SP. So staring at the approximation error term itself, it shows a trade-off between the flexibility of the basis function class, which can make the approximation error smaller, and the condition number, which might get larger as you increase the flexibility. So there's some kind of trade-off between the condition number and the value of epsilon star SP, just looking at that term. But overall, looking at the entire bound, right, this bound provides a recipe for convergence, right? So To be able to apply our method and actually produce an epsilon solution path, we need to be able to bound both terms and understand the trade-off between driving the first term down to zero with a stochastic optimization algorithm and driving the second term down to zero through approximation theory, right? Through the choice of approximation of basis functions and their corresponding approximation errors. So let me sort of illustrate that with an example, right? Or two examples. One example of how to bound the optimization error, and then another example of how to bound the approximation error, right? So to bound the optimization error, and maybe also point out one final thing about this bound. So on the surface, the bound perhaps also seems a little bit counterintuitive because it seems almost like impossible to bound a worst case sort of metric in terms of an expected metric, right? So it seems like a miracle in some sort of way. But it's important to note that the bound says we can do no better than the approximation error, right? So the bound can be interpreted as when the approximation error is small, when you can actually identify a good model, then you're able to identify such a good model by solving a stochastic optimization formulation. It's very similar to, for example, in linear regression, when the data exactly satisfies a linear relationship, then 2 points are enough to determine that linear relationship, right? Or more generally, when the data satisfies some sort of approximate kind of polynomial relationship or something, a relatively small number of data points may be needed to determine a good approximation to that polynomial. So there's no miracle here, right? Because we're converging up to the level of the approximation error. Okay, now let me show, as I said, two examples of how to bound these terms. So first, for the optimization error, we will use SGD and rely on convergence theory of SGD in something called the near interpolation regime. Then for the approximation error, we'll look specifically at the case of polynomial basis functions and use some results on function approximation theory on polynomial interpolants to be able to bound that. Okay, so in a nutshell, here's the result on optimization error. Essentially, if we run stochastic gradient descent with appropriately tuned step size, then we can show that optimization error term converges linearly, right, exponentially fast to zero. Meanwhile, the approximation error term remains. So what this result is showing is that we have very fast convergence up to the level of the approximation error. Right, so that optimization error term is converging linearly, while the approximation error term is a static sort of constant for any fixed basis function class. So this is very good. It means we can drive the optimization error down to zero very quickly. But on the other hand, we are left with this approximation error term. So this sort of naturally leads to an idea of an adaptive basis algorithm. But first, let's just sort of visualize this kind of convergence in practice. So this is a sort of preview of the numerical results. And what we see here, the dashed lines basically show our algorithm for different polynomial degrees, 5, 7, and 9. And as we increase the polynomial degree, basically the approximation error gets smaller. And for each of them, optimization error sort of relatively quickly converges to that level of approximation error. But then once it reaches that level of approximation error, it sort of levels off, right? And it bounces up and down at a constant value that's proportional to that approximation error. So that kind of naturally, motivates an adaptive algorithm which tries to detect when you are leveling off, and then iteratively adds new basis functions, right? It adds higher degree polynomials, for example. So we do propose such an adaptive algorithm. And this is just, formally the adaptive algorithm, but it's a very simple idea, right? You start with, essentially one basis function, and then once that, your current set of basis functions converges to the level of approximation error, and you run some test to try to detect that, then you increase the flexibility of the basis function class by adding higher degree polynomials, for example, and continue to run your stochastic optimization algorithm, so on and so forth. So we call this ALSP, adaptive learning the solution path, and that's what's shown in orange here, and it's converging rather rapidly on this example. Okay, to analyze the approximation error before I show those numerical results in full detail, I want to give one example of how to analyze the approximation error using approximation theory for polynomials. So for this, let's just assume for simplicity, we are talking about the one-dimensional case. So lambda is minus 1, 1, normalized without loss of generality. And we'll approximate each of the components of okay, sorry, there's only one degree here. So we just have dealing with, sorry, only one component. So we're just dealing with d equals 1. And we approximate the optimal solution theta star, which is a scalar, by a degree at most q polynomial. Yeah, in general, that means that the matrix here is block diagonal, but here we're just dealing with one block. Okay, so we have a theorem which bounds the approximation error. It's quite a complicated theorem, lemma, I should say, because it's really just an application of this theorem from a polynomial approximation theory. Importantly, this lemma basically shows that as you increase the degree of the polynomial, the approximation error shrinks and it goes to 0. As long as you're above the level of smoothness of your current of the theta star function, right? Of the actual true optimal solution function. So so the details of that lemma are not so important. The important thing is that in a nutshell, what our results show here in this specific case of this scalar lambda and using a basis of Legendre polynomials, and also the distribution is uniform. Our results basically show that when theta star, the true optimal solution mapping, is nu times differentiable, so it has some inherent smoothness, or even if it has analytic properties, so it's infinitely smooth, then our algorithm strictly outperforms the best known results for naive discretization in theory, right? So so as long as nu is greater than or equal to 3, the number of basis functions and the number of basis functions is given for our algorithm, but importantly, the number of gradient calls required for our algorithm strictly improves upon the number of gradient calls required for discretization, right? So discretization will solve each optimization problem independently using a separate stochastic gradient descent for each problem. Here we solve the global problem with one stochastic gradient algorithm, and our total number of gradient iterations is strictly better than the discretization approach as long as theta star is sufficiently smooth, right? As long as nu is greater than or equal to 3. Okay, let me show the results of the numerical experiments. So here we first consider a reweighted logistic regression on an imbalanced binary classification data set for law school bar exam prediction, whether they'll pass this bar exam. So this has 45 features and 1,000 observations. So specifically, we consider logistic regression with regularization, and the parameter lambda is a single parameter that trades off on the logistic loss on positive class versus negative class. And so lambda is a scalar between 0 and 1. Our basis functions will be, again, these Legendre polynomials, and we'll also try Jacobi polynomials, which are an extension of the Legendre. The algorithm will be stochastic gradient descent, and the benchmark is uniform discretization. We warm start it, so we allow it to use previous solutions to warm start the next solution. And we tune the number of discretization points roughly according to the theory by setting this parameter delta, which can be thought of as an accuracy parameter, and setting the number of discretization points proportional to 1 over square root of delta. Okay, so these are the results then, and it's actually the figure that I showed you before, plus another figure. So A is the case of Legendre, that's the figure I showed before, and what we see is that as long as the basis functions are flexible enough, so Q is large enough, the degree of the polynomial, then we outperform uniform discretization by quickly identifying a solution that has better solution path error and less gradient calls. And that's true of Q equals 7, Q equals 9. It's also certainly true of the adaptive method, which very quickly converges in the case of Legendre. So it very quickly identifies when to add new basis functions and really only requires a small number of gradient calls, relatively speaking, to find a solution with a very small solution path error. For Jacobi polynomials, the results are similar and a little bit less behaved because Legendre turns out to be a better choice for this application. Let me show results on a more complicated problem. So this is portfolio allocation on the Fama French data. So here we have two parameters, lambda 1, lambda 2, controlling return and variance terms in the portfolio optimization. We consider an unconstrained portfolio optimization, so we allow short selling and unboundedness of the portfolio weight. So it's a little bit unrealistic, but it's a sort of stylized portfolio problem. And we also have an L1 smooth approximation to L1, which encourages sparsity of the portfolio. So again, we consider Legendre polynomials. We now apply LBFGS instead of SGD just to try a different algorithm, and discretization is tuned in the same way. So we see sort of similar results as before, with the adaptive method performing perhaps a little bit less well as the ideal case from before. But again, we sort of see that we're, for the most part, outperforming uniform discretization pretty strongly. We also tried a high-dimensional extension of the portfolio problem where we include also a term that penalizes the squared distance from a reference portfolio, where this reference portfolio is represented by this lambda 3 through 12, right? The third through 12th component of the lambda parameter vector. So now we're dealing with a 12-dimensional lambda. For this, we chose a very specific basis function that I won't get into the details of. In the high-dimensional case, it becomes hard to even evaluate the solution path error. So instead of doing that, we computed a Monte Carlo, SAA type of approximation, where we did. So first of all, for our algorithm, we did SAA. So we solved this SAA problem. And we tested the performance also on an independent validation set of the same size of 1,000. And so these figures show the comparison to the performance of the oracle on that validation set. So the dashed curve in gray at the bottom is the average on the validation set optimal value. And that's sort of the oracle on this validation set, the best error that you can achieve. And we see that as we increase the degree of our polynomial, our methods are converging towards that oracle level. So this is essentially an example to show that our method converges. We don't compare the solution path error to discretization because it's too hard to compute the solution path error in this high-dimensional case. But we at least see that our algorithm has some reasonable convergence properties, right? So it's converging to the oracle level on an out-of-sample validation set, as seen here. Okay, briefly, I'll just mention some related work. So joint with one of my students, we have looked at an extension or a related problem in robust optimization. So here we look at applying a similar learning the solution map idea to a robust optimization problem with robust constraints. However, for that problem, we're dealing with constraints, so we introduce a penalty function. And there's less theory, but we have some computational results on knapsack and inventory management problems. Also with a former student, Heywan, I have some specialized results in the one-dimensional case based on an ordinary differential equation characterization for the solution path, which also leverages the smoothness to get some nice results above naive discretization. In conclusion, this learning the solution path algorithm is a flexible approach that can give a recipe for how to solve parametric optimization problems across all values of the parameter by reframing as a single stochastic optimization problem. And our results sort of nicely show the relationship between stochastic optimization error, approximation error, and the solution path error, which we ultimately care about. In practice, we see some good results in our examples, and certainly more work to be done on more examples in the future, as well as more complicated learning methods like deep neural networks or forests of boosted trees, as well as stronger theoretical understanding of learning methods for more complicated optimization models, including robust and other constrained optimization models. So with that, here are the references, and just thank you for your attention, and I'm happy to take any questions.